Dr. Sanket Joshi recommended your name for this workshop, and you kindly agreed to be present for this introductory talk on spectroscopy, UV visible, IR, and NMR. So thank you very much. What is the time there right now?
It's 8:30 in the morning.
8:30 in the morning. Oh, okay.
Yeah. 1.5 hours behind.
Here it is 10 o'clock.
Yes.
1.5 hours, I think.
1.5 hours behind, yes, Professor.
And you are in which country?
I'm in Muscat.
Muscat.
Oman.
Oman. Wow. Thank you very much. So welcome.
Yeah.
Sanket, could you briefly introduce Dr. Samuel to the audience, and then he can start his talk. Right.
So good morning from India, Dr. Prem. It's so nice to seeing you virtually again. So just to give a brief overview about Dr. Prem. After completing his PhD from India, he went to Italy. He worked on different kinds of R&D projects, and he was doing his postdoc for 3 years in University of Torino in Italy, where he worked on synthesizing hyperpolarized contrasting agents for MRI to visualize tumor cells. So he is having more than 18 years of experience with a chemistry background and worked on multidisciplinary. So after completing his postdoc for 3 years in University of Torino, he worked on different pharma-based projects in Italy, in France, and in different companies from Germany and Italy. And after completing it, he worked in Claudi SRL Italy as a research scientist R&D for 3 years, where he designed, characterized, and synthesized different kinds of fluorescent dye derivatives and pharmaceutical-based contract research based on API. After which he came to Muscat, where I know him for almost past 15 years. So he has joined the Central Analytical and Applied Research Unit, and he was also teaching in organic chemistry in College of Science for a few years. And so he is an expert on chromatography, basically, different kinds of mass spectrometry and NMR. At the same time, he is also ISO quality manager. He is taking care of ISO 9001 for CARU in SQ, and he is an application training specialist. And he is handling NMR, HPLC, LCMS, MALDI, FTIR, UV visible, HPTLC. List is long, CHNS, and everything. So thank you, Dr. Prem, for coming virtually and enlightening our all the participants. So the floor is yours. Go ahead, please. Thank you.
Yeah, thank you, Dr. Sanket, and thank you, Professor Kothari. It's an honor to come and present my slides here. Yeah, so you can see my screen, right?
Yes, it is visible.
Yeah, so I'll make it a full screen. Okay, so I'm going to just make it as interesting as possible because I know like people are from varied backgrounds, and so I'm going to touch very important theory which is needed for your practical application, which you're going to do later also. And I'm going to introduce about basics about spectroscopy, what do you mean by spectroscopy in a very simple term. And then I'm going to just talk about UV visible and a little bit of nanodrop spectrophotometer, and then FTIR and NMR. Like I will try to finish everything as soon as possible. I will skip some slides, which is not very necessary, but anyway, on the flow, like I will concentrate on most of the things. So as Dr. Sanket said, I'm working in a Central Analytical and Applied Research Unit in Muscat, Oman. And we have around 17 big, advanced latest instruments here. So, okay. So now into the spectroscopy. Yeah, what is spectroscopy? So spectroscopy is a study of interaction of matter with electromagnetic radiation. So that's the basics, right? So see, there is a saying in our place that, see, when you want to fish fishing from a pond, if the pond is calm, you cannot know, you will not know exactly what is the content of the pond, right? So first you have to like perturb it, disturb the pond so that you will see all the fishes moving in, and then you can easily fish in. right? So that is the same thing we are going to do in spectroscopy, right? The molecule is going to be in a stable form, right? So we are going to use a physical stimulus. Okay, so depending on different electromagnetic radiation, the molecule is going to respond in a different way. And this response is going to be detected by a detector specific to the instrument. And then the output can be a spectrum or a digital meter or a reading. Okay, so that's the thing, right? So what can be the effect? What can be the effect of the electromagnetic matter on, like when electromagnetic radiation falls on a matter, it can either pass through, or it can get reflected, or it can get scattered, it can get absorbed, it can get refracted, depending on the substrate in which we are working on. Okay, so this is a very broad spectrum idea of electromagnetic radiation, right? So we know, we have heard about many terms in our day-to-day life, like microwave, right? Everybody uses microwave now, right? Radio, everybody has used FM station, right? So these are the broad classification, right? From the lower wavelength to a higher wavelength in meters, gamma rays, X-rays, ultraviolet, visible, infrared, microwave, and radio. So today, the concept what I'm going to talk about involves UV, ultraviolet, visible, infrared, and radio. Okay, we're going to just see what is happening in the molecule when you expose these molecules with these kind of electromagnetic radiation. Okay, just for an example, like since we are using UV today, UV is going to impart electronic transitions, right? So there's, when you pass UV to a molecule, the electron is going to jump from the lower state, ground state, to the higher state, excited states. Okay, so this is the idea behind it. So when you use visible and infrared, it's going to be molecular vibration. So there is going to be a transition between the vibration from the ground state to the upper state. Okay, so I'll make it all the terms very simple. Like always, we are going to talk about ground state, excited state. So when the molecule absorbs the electromagnetic radiation, it's going to move to the excited state. Okay, so this is what we are going to measure as a final output. Okay, and then we are going to use radio frequency. And then the radio thing is used for nuclear transition. So that's where the NMR comes into play. Okay, so in nuclear transition, it's going to be again a ground state transition from nuclear transition from one ground state to the excited state. So that's the idea behind the overall spectroscopy. Okay, so a spectrometer is a device which is used to record or study this properties. Okay, the plot of a particular property against wavelength, frequency, energy of radiation is called spectrum. So we get a spectrum out of it, and we try to interpret the spectrum accordingly. Okay, so that's the main thing. The spectrophotometer is used to measure light. Okay, so the main idea is to spectrophotometer. So photo talks about light, so it's going to absorb your light, or it is going to show something related to light and wavelength here. For example, in an UV instrument, okay, so we are going to measure the intensity of the transmitted light compared to the intensity of the incident light beam. So this fraction, we call it as transmittance. Okay, transmittance is a very common term which we use in FTIR. Okay, so absorption is a very important, very common term which we use in UV visible spectroscopy. Okay, so now into the UV visible spectroscopy, right? So this is a picture of Carry 60 UV visible, which is manufactured by Agilent. So this is what we are using in our laboratory. So I just took a picture of it. Yeah. So UV spectroscopy, again, you know the range. Okay, so we are going to cover a range from 200 nanometer to around 800 nanometer. So that we call it as the UV visible range. Okay, so okay, if you talk about, okay, there are three kinds of UV. We call it as UVA, UVB, UVC. Okay, UVC and UVB are shorter wavelengths. Okay, so most of them get deflected by ozone itself, so it's not coming into the Earth atmosphere. Okay, UVB slightly comes, like around 5% comes through the pass through the atmosphere and comes to the Earth atmosphere. Okay, so that causes the sunburn, and then we also have the UVA, which is deep and penetrating, which causes wrinkles, aging, spots in our body, right? So these are the region with 3 types of UV, and then we are going to, so the range in which we are going to concentrate is from around 200 nanometer to 800 nanometer. Okay, whenever we talk about UV visible spectroscopy. So another thing which we should understand is, see, when a sample is observed, okay, so we will always see a complementary color. Okay, so when violet is observed, we'll see yellow green. When blue is observed, you're going to see an yellow color as a complementary color. So this is just an information for you. Okay. Okay, so now we will get an absorption spectra in an UV visible spectrum. So I spoke about the electronic transition. You know that. Okay, whenever we talk about atoms are different electron levels. Okay, so jumping from the lower level, wherever the electron is now placed, after absorbing the UV visible radiation, it goes to the next level. Okay, so this transition is what is recorded as a UV or absorption spectra in UV visible spectrum. Okay, so the maximum energy what we need to do this transition in a UV visible range is around 1.5 to 6.2 electron volt. Okay, so which is related to wave number 200 nanometer to 800. So whenever we talk about UV visible spectroscopy, the one more important thing which comes up is the Beer-Lambert's law. Okay, Beer-Lambert's law is a very important principle which is used to calculate the concentration. So UV visible spectroscopy can be used to determine the concentration of the dissolved substrate in solution, right? So that is also a very important. So what are the thing which we will get in beads? The principle is that for a single wavelength A, okay, we call it as absorbance, whatever we record in the UV visible spectrophotometer. Okay, and that doesn't have any units. Okay, and epsilon is the molar absorptivity of the compound or molecule in solution. Okay, so that is a constant for a particular solution. Okay, and B is the path length of the cuvette. Okay, so we'll be using a silica cuvette or maybe a plastic cuvette. Okay, use and through cuvette, or maybe we can use quartz cuvette. Okay, so normally the length for a normal measurement will be around 1 centimeter path length. Okay, and C is the concentration of the solution. So if you know the other 3 values, you can easily concentrate you can find out the concentration of a solution. Okay, so this is useful in finding out the concentration of protein, right? Peptides, amino acids. Okay, so dyes. Okay, so we can easily find out using this Beer-Lambert's law. So Beer-Lambert's law is a very, very important basis for this UV visible spectrum when you talk about quantitative analysis. So the main thing is we need a light source. Okay, so that's what we call the electromagnetic source. Okay, here we're going to use an UV source. Okay, then we need some place to keep our samples. We call it a sample holder, and then we need a detector to detect it. Okay, in case of you are measuring only on a particular wavelength, then you might need a monochromator or a filter, so on. Okay, so in our system, like in Agilent Carry 60, what I am using currently here, we use xenon flash lamp. Okay, so that gives a very good output in this range from 200 nanometer to 800 nanometer. Okay, so there are 2 types of UV, which we call it as a single beam instruments and double beam instrument. Okay, in the single beam instrument, you can see that directly the light falls on the monochromator and then to the sample and then to the detector. But in the double beam system, right, you have to keep a reference. But in the the single beam system, you have to place your reference first, okay, run the reference as a blank, and then you have to run the your main sample as your sample. So the reference will be always the same solution what you are using, except the solvent. We can say the solvent which you are using, except the protein or peptide or amino acid or whatever you are looking for. Okay, so that's the idea behind these two. But now the latest development uses simultaneous instrument. That is, you don't need a monochromator now. Okay, simultaneously we have a diode array detector which can detect all the wavelengths which is emitted by the sample, like which is passing through the sample and all that, right? Okay. So the light source, what we commonly use is a xenon flash lamp source. Okay, so the benefit of using the source is because there is no photo degradation, because some compounds are very receptive to photo degradation. Like when you expose it to light, it can degrade and form a different compound. So that can lead you to a different conclusion. So therefore, xenon lamps are very good in case of that, if you don't want to see any photo degradation. Okay, there are other lamps also, halogen lamps. There are many, many kinds of lamps which are used. So we are using a xenon lamp, which can give you better results compared to the other lamps. Okay, and then it requires zero warm up, because if you see a normal UV visible, you have to just warm the light lamp for at least few hours before running a stable to get a stable output. Okay, but now this one xenon flash lamp picks up very quickly. You don't need much time to wait for the system to get stabilized. Okay, and then we use a diffraction grating. I already explained, because we are going to measure simultaneously wavelengths from between 200 to 800 nanometer. And then we are going to use a silicon photo iodide detector. Okay, so this one, basically when the light falls on the detector, it's going to convert the light into electricity. And then finally, it's going to give you a value for absorbance or transmittance. So this is the idea behind this. Okay, so you can see the cuvettes. Here there are a lot of cuvettes which I've shown. Depending on your application, depending on your instrument, you can use different kinds of cuvettes which we can use. So we can see that only there is two sides which are transparent. The other two sides are opaque. So always make sure that the sides which are transparent faces the source, okay, to get the optimal results. Okay, so we normally use quartz or fused silica. Okay, when you want to use only for the UV, you can use silicate glass if you are measuring between 375 to 2000 is too much, so we can go up to 800 for our discussion. And then we can, now the latest thing is the plastic cells. Okay, if you're not using any organic solvents, if you're using water and all that, it's an use and throw plastic cell. You can just put it, you don't need to clean, just throw it out after your overall experiment is over. Okay, because the other things are all reusable, so you have to clean it properly to make sure that you don't leave any residue of the previous compound measured. Okay, the most common cell path we are going to use is around 1 centimeter. Okay, so the one more thing what you should understand here is, like, the solvents what we use are also going to absorb in the UV range. Okay, we call them as lambda max of the solvent or UV cutoff, right? So I have given some examples, like the common one, like water 190, okay, methanol 205. Okay, so suppose if your compound is soluble in two different solvents, then it's better to choose a solvent which doesn't interact with your, which doesn't come in the place of where your spectrum you're looking for, where your absorption is. Okay, so therefore we can choose the right solvent. So that also plays a very vital role in getting a wonderful output out of UV visible spectrophotometer. Okay, so some of the important terms which we always talk about. Okay, I'm not going into the lot of depth chemistry into it, but just these terms are very commonly used whenever we talk about UV spectrum, right? Chromophores. Okay, chromophores are nothing but unsaturated. Unsaturated means double bond, triple bond. Okay, so unsaturated compounds, functional groups can absorb ultraviolet or visible range. So I've given some example, like for example, carbonyl, C double bond O, you will absorbs up 280 nanometer. Okay, if you see benzene, Okay, again, it goes to, it absorbs at 261 nanometer, right? So conjugated trine. Okay, so different, like, so as long as there is unsaturation in a molecule, there's going to be a better absorption in the UV visible range, what we are looking for. Then the other one, we call it as the oxochromes. Oxochromes are nothing but functional groups like OH, which has some additional unshared pair of electrons. So oxygen has two lone pair of electrons on it, right? So these are called unshared pairs. This is not used for bond formation. That's why we call it as unshared pairs. Okay, so NH, SH, etc. So this can create a shift in the absorption. If these kinds of functional groups are present in your molecule for which you are going to see the UV visible spectrum, there is going to be a shift to a longer lambda max. So this we call it as a bathochromic shift. And if the shift is going towards the shorter lambda, then we call it as the hypsochromic or the blue shift. Okay, so red shift, blue shift. Okay, depending on, so you might expect your compound coming at 250 nanometer, but you will not see it at 250, but you'll be seeing at 255 or 260, depending on the different functional groups in your present in the oxochromes present in your system. Okay, so what is the uses of why we use UV visible spectrum? The main thing is detection of molecular structure. Okay, we can just understand, okay, if there is chromophores in your molecule, okay, we know that we can easily find them in the UV range, okay, and then we can also do a quantitative measurements, okay. I'll be just showing some few examples which I worked on with quantitative analysis, so it will be very useful and like interesting for you. And so as we are going to employ the Lambert's law to understand calculate the concentration of the solution. So it's mainly used in pharmaceutical, chemistry, and even in biology, right? So and identification purity testing also. So you can see, suppose you know this compound and you know this lambda max, and if you don't get it at the same place, or if you get an extra absorption, that means there is some impurity which is present in your samples. These are very simple tests. Within few minutes you can get an idea about what is the system, whether it's a pure system or something which is there in the system. It's a mixed system, so it gives you a very good idea. So even the chemists, they use for monitoring the reactions also, right? So whenever you perform a chemical reaction, you want to just see a functional group change or something changes in your molecule, then you can just see whether the reaction is proceeding in the forward direction. There is a change in the absorption or not. So these are very simple and primitive techniques which is helping us to understand whether we are moving in the right direction. Okay, so I've not talked much about this, but just you should know about this in basic level, like sigma electrons or the electrons in a saturated carbon. Okay, saturated compounds, right? Like some CH3, CH2, CH2, like that. Like ethanol is a saturated compound, right? So pi electrons in unsaturated compounds, right? When a double bond, triple bond, we always say that electrons which are forming the bonds are called pi electrons. And N electrons are the ones which is the non-bounded or the lone pair of electron which is available on the atom. Like in oxygen has two lone pairs of electrons. Okay, so this transition, always remember that whenever the molecule is going to absorb the UV light or any light, electromagnetic radiation, it's going to move from the ground state to the lower state. So for example, if you take the sigma, so sigma is the lower state and sigma star is the excited state. Okay, the transition between them. Okay, so accordingly, theoretically, we can have around 6 kinds of transition possible. Okay. So the other thing what we should know here is these transition has different energies and therefore different wavelengths. Okay, so that's why, see, all the molecular transition or maybe nuclear transition, electronic transition, all occurs based on energy. Okay, it depends on all the whole reaction stability and everything is based on energy. So if there is too much energy needed, that will not be, that will be very difficult to undergo that kind of transition. So normally the sigma to sigma star transitions are very difficult to find, but it can happen depending on the energy level of the molecule. But most of the time we look into n pi star and pi star transitions are very common in practice in the range what we are looking for. For example, sigma sigma transition, if you see, right, we have, if you take a methane, a compound methane, okay, it has only saturated bonds, CH, okay. So only sigma transition is possible, sigma to sigma star transition. So therefore the absorption maximum will be around 125 nanometer. So we cannot see in our normal UV visible spectrum. Okay, so therefore, when you run a methane is a gas actually, right? So any saturated small compounds, if you run it, you will not see any absorption maximum except for solvent. Okay, so because our range for UV visible is from 200 to 800 nanometer. Okay, so normally it is not seen here. So if you see the N to sigma star transition, okay, it is happening in saturated compound containing lone pair of electrons. Okay, so this will occur in between 150 to 250 nanometer. Okay, and the peaks are very small. As I told before, it all depends on energy, whether the molecule is able to undergo this kind of transition. Okay, so the most common one what we use here is the N to pi star and the pi to pi star transition, which comes under 200 to 700 nanometer scale, right? So these transition needs an unsaturated group in the molecule. So always you need an unsaturated compounds are very highly visible in the UV visible spectrum. Okay, so the transition I have marked here in the green, N to pi star and pi to pi star. You can see the energy, relative energy is very less. So almost all the unsaturated compounds can easily undergo this kind of transition. Okay, so the main factors affecting is the solvent. Okay, the solvent what we are using is going to play a very important role. Some solvents are very neutral. Okay, it's not going to interact with your molecule, and therefore there's not going to be any shift in the lambda max. But for example, when you are using a solution in ethanol, your sample is dissolved in ethanol, and then you are taking the UV spectrum. Okay, there can be a shift to longer lambda max, lambda value. Okay, so the changing in polarity plays a very important, like non-polar solvents like hexane is not going to play very important role in this kind of shifting. So you are going to get where, so even be considerate, because as a biologist, you will be also doing a lot of extraction and buffer. Okay, when you're seeing protein, normally in buffer-based solutions, right? So be careful to know about the absorption of the buffer also. Okay, where the absorption this buffer, lambda max of this buffer comes, and whether it's coming in the same region where you're looking for. Okay, so normally when we look for protein, we'll be looking at 280 nanometer. Okay, so you should be clear that the buffer doesn't have any absorption lambda max in this particular range to estimate the real correct concentration of the protein. Okay. And also the experiment has to be performed in a constant temperature. Normally we perform at a room temperature. Okay, so you have to perform at a constant temperature. Temperature should not be varying, so that should also affect your final output. Okay, so for example, I've given you many examples here, but not I'm going to touch all the examples. But here, if you see the blue ones here, lambda max 178 nanometer. If you see the conjugated one, which is below similar molecule, but the double bonds are alternating. But in the first case, a double bond is not alternating. So whenever they have a conjugated system, okay, the electrons are freely moving. Okay, the lambda max is going to be shifted to the higher lambda max. So we are going to get 227 nanometer instead of 178. If you see the molecular composition, almost it's very similar. Arrangement of atom, number of atoms are same. Okay, number of double bonds are same, but only thing is the below one is conjugated and the other upper one is not conjugated. Okay, so some of the applications. Okay, so quickly into the application side, right? See, we have the main thing is to see any compounds which absorbs in the UV and visible range. So I have taken an organic dye called rose Bengal just for easy observation, right? Rose Bengal absorbs around 500 and 570 nanometer, around 500 to 600 nanometer. See, whenever you want to do the quantitative analysis, then you have to dissolve the sample in different concentration. Okay, like for example, we have run around 5 ppm, okay, 5 micromolar, 10 micromolar, around 20, 30 micromolar. We have prepared a solution first and we have done a calibration curve. Okay, so then you can place your unknown sample concentration, which doesn't have a concentration. You can place it here and then you can find it out. So you can see there is two absorption. One is on the solvent absorption. You can see it in the near UV region, near closer to 200 nanometer. And then because it's an organic dye, dyes normally have a visible. So that's why range. So that's why we see a color from the dyes, right? So therefore, it comes in the visible range. Okay, so this is a very common application, right? Even for to find out whether your protein, right, is a random coil or alpha helix, or whether it is aggregated. Okay, so easily we can find by the concentration of the protein. So when you put the protein, and if it is random coil, the concentration of that same thing is going to be higher compared to the lower thing. See, if aggregation happens, then the adsorption is going to come down, and therefore the concentration of your sample is going to be, the absorption is going to be lower also. So there is some reference here. You can also read through this paper for a full complete information, right? So, and then for example, caffeine. Okay, so these type of analysis which we did in our lab, right? And so I have quoted a paper, okay, very similar to where they are doing this kind of analysis. You can go through this. See, caffeine adsorbs at around 272 nanometer. So we can again do a calibration curve with different ppms, 10 ppm, 20 ppm of caffeine, 30 ppm, 40 ppm, 50 ppm. So you can see the difference of the curves, right? So the 10 ppm, you can see a lower, the lighter blue, and the 50 ppm is a darker blue on the top, right? So as the concentration increases, the absorption increases. The concentration and absorption are directly proportional. Okay, so then with this data, we can easily go into the data for the whatever coffee you're analyzing. So we analyze the coffee, okay, and then we can see the adsorption. So from the adsorption, you can understand what is the ppm of each and every compound. See, even by roasting temperature, like even if you see the pure Arabica, right, 195 degree and 250 degree, so there is a big difference in the value, right, adsorption. So that means the caffeine is getting burnt out or decomposed or degraded because of the heat. So we don't see a very high absorption maximum for caffeine. It is only 0.387 nanometer. Sorry, it's 0.387. And if you see at 195 degree, you see the highest concentration of caffeine, 1.123. So that's why the roasting temperature of a coffee is also very, very important. So this technique will let you know if you've done the calibration curve and keep it ready, you can find the data and understand the output of the of your coffee, the nature of your coffee, the amount of caffeine in just few minutes, like 2-3 minutes. That's why these techniques are very, very vital till now, even though we have sophisticated analytical instruments, but these instruments are very, very useful in getting very good data out of it, right? So one more thing about the amino acids, right? So each amino acid adsorb in a different region. Okay, cysteine around 204 to 220, then phenylalanine 250 to 265. Okay, and histidine, it comes about 312, right? So we can just dissolve your sample and check whether these amino acids are present. If there is amino acid present, you will be seeing a band. If you have a multiple mix, then you are going to see multiple bands at different wave number. So if you can make a quantitative study, you can make a quantitative study, or you can just qualitatively say whether this amino acid is present in a particular footstep. So that's what. So you can also go through this article which I've placed it down. So this will help you to understand more better. So these are some of the examples. They are just saying plus means present, negative means it's not present. So it's very easy with an UV visible to, even the sample preparation, very simple. Okay, you have to prepare the sample, dissolve it in a right solvent, and then you have to record your spectrum. So even the recording, the modern recording speed of the UV visible is only less than the 10 seconds or 20 seconds. You can record a full spectrum in the range of 200 to 800 nanometers. Okay, so you don't need a monochromator, but you can use the modern technology to simultaneously do the UV application. Okay, so into the nano drop, right? Nano drop is nothing but an extension of the UV visible spectrum. Okay, so here what is the advantage here is mainly it is used for concentration of DNA, RNA, and protein. Here we are going to use only 2 microliter solution. See, normal UV visible, we need around 4 ml to 10 ml solution. Okay, even 5 ml, even 2 ml. Okay, depending on the cuvette which we are going to use and what our system holds, right? But the nano drop, you need only 2 microliter. 2 microliter is nothing but a 1 drop. Okay, so the speed of analysis is going to be fast. Okay, and even cleaning and doing the next sample is going to be very, very fast. Okay. See, again, we are going to use whenever you want to use nucleic acid calculation for nucleic acid, okay, we are going to use the Beer-Lambert's law. Okay. So as I told you before, the epsilon value is a constant depending on what solution you're going to use. So here they're using double standard DNA. So 50 nanogram per centimeter per microliter is the epsilon value what we are going to. Single standard means 33 nanogram. RNA 40 nanogram. Okay, so you have to find the absorption, okay, and substitute in this equation. You will get the concentration. Okay, B is the path length. Normally we use 1. So therefore, absorption into epsilon will give you the final data for concentration. It's very, very simple. Okay, so the one of the thing what you should be very careful about is the adsorptions, right? We have to look into 3 regions. One is the 260 nanometer range, one is the 280 nanometer range, and one is the 230 nanometer range, right? So in 260 nanometer range, we normally see the nucleic acid absorption, right? Because of the purines, thymine, cysteine, and uracil, pyrimidines, everything they absorb around 260 nanometer. So whatever absorption you are getting there is going to be due to nucleic acid. Absorption at 280 nanometer is going to be your protein, right? So aromatic, the mainly aromatic amino acids which are present in the protein is going to absorb at the range of around 280 nanometer. And absorption of 230 nanometer or something related to your buffer, the other solvents and all that, right? So you should be very careful in estimation. So always you have to make sure that you take a ratio of different proportion. Like for example, if you take absorption from 260 and absorption and divided by 2 absorption at 280, you will get the ratio of pure RNA and DNA, nucleic acid. Okay, if there is any DNA contamination, then the ratios are going to vary. If you have going to have a higher ratio, then that means you are having a pure nucleic acid. So if the ratios are going to be lesser and lesser, that means there is a contamination of other substrates. Okay, so this is a chart just showing. Okay, so you can also take another ratio, okay, of 260 by 230 also. Okay, 230 gives you an idea about other organic contaminants. Okay, you can also take that ratio also and then see whether it's fine or not. Okay, so only this data is needed when you need it to do for a quantitative analysis. For qualitative analysis, you don't need to know whether this absorption is a mixed absorption or not. But when you are working for a quantitative analysis, to make sure that you get the right concentration, you have to eliminate this ratio. So you have to do this ratio to check whether everything is fine or not. Okay. So now into FTIR, right? So now we are into the FTIR spectroscopy. Okay. So whenever we talk about FTIR, okay, there are two types of FTIR. Okay, the classic FTIR. This was the only FTIR available when we were studying about this in our college days. But we now commonly use the ATR, FTIR. Okay, I will explain the difference and all that in a very short moment. Right. So you can see the above picture is called the ATR FTIR. Okay, very simple to use. And the below one is a classic FTIR where you mix your sample with KBR, okay, grind it and make it into a pellet. Okay, the pellet has to be transparent, okay, because you're going to measure the transmittance, what amount of IR radiation is going to pass through the transmittance and reaching out the detector. So if the transmittance is not good, the quality of output is auto. FTIR spectrum is also going to be very, very bad. Okay, so this is the idea behind the classic FTIR. So in ATR FTIR, you don't need any sample preparation. Okay, you can suppose somebody is saying, okay, they're bringing some plastic material to you and you want to just check the plastic. What is this? Just keep the plastic paper inside and then you can run the spectrum immediately. And it's going to be very fast, no preparation. It's going to be very, very straightforward. Okay, only disadvantages, right? The penetration depth is going to be different. So it is, if you see the classical one, because the light passed through that, it is passing through the whole sample. Okay, so it's around 1 to 10 micrometer. And if you see the ATR FTR, it's going to be 0.5 to 2 micro, because you're going to place your sample on the top of a crystal. The sample is going to be on the top of the crystal, and the light is going to pass through the crystal and touch the. So therefore, the penetration depth is less, but anyway, you can see, depending on the application, we can use it for a very straightforward and quick application. And even you can create a library with ATR, FTR, because the reproducibility is going to be very similar. Because in KBR, if there is any impurity in KBR, it's going to affect your overall quality of the pellet. And if you're not giving, like you're not having a proper composition of the sample, then that's going to affect the quality of the spectrum. But here, it's straightforward. You're going to just place your sample on the crystal, and whether it's liquid or solid, and you're going to record the spectrum. Okay. So only thing is, disadvantage we can say is lower sensitivity in case of ATR. But it is, that sensitivity is useful, is okay for most of the applications what we are doing. Even we have created our own library using this standard materials, drugs, plastics, and all that in our laboratory, so that whenever we get some plastics like microplastics and all that, so we can easily identify what is the composition of this plastic using our library to enhance our confidence. Okay, so again into the wavelength region, right? So we are going to talk about IR range, right? So between 4000 nanometer, we can say, to around 400 nanometer. Okay, 4000 to 400 nanometer. So in between the UV and the microwave region. Okay, so what happens to when the molecules or the substrate is exposed to IR radiation, it's going to vibrate your molecule. So there's going to be a transition from a lower vibrational state to a higher vibrational state. So that's what we are going to record. In UV, it is the molecular transition, right? Electronic transition from one level to the upper excited state level. Okay, so that's what we are going to see here. It's a vibrational levels. Okay, so this is a common classical FTIR, right? You have a source, you keep your sample as a pellet, and it reaches the detector. So transmittance. So your sample should be transparent enough to pass the IR light and then reach the detector. So that gives you the quality of the classical FTIR. Okay. Sorry. Okay. So this is the ATR, FTR, which is in the downside, left side of your speaker in the screen. Right. So normally we have a diamond crystal. What is ATR means? Attenuated total reflectance. So the classical FTR is using transmittance. Here we are using reflectance. So you can see the source of light is in an angle with the sample. So the dark blue part, semi-solid, is a sample. And you can see the diamond crystal. So diamond crystal is where we are going to place the sample in. And then it's going to reach the sample and then reach as the detector. So multiple reflectance are going to be summed up, and then you're going to get the final spectrum. Okay, so it's a very easy technology, easy to clean. There are many crystals like germanium, then zinc, selenium crystals. Okay, so depending on application, you can choose your application. So we are using diamond crystal because diamond is resistant to pH. Okay, and we can use highly acidic substrate, or we can use even very highly basic substrate. Nothing happens to the crystal. It's very rigid because ours is a research and analytical company where we also do for petroleum related people. So we get a lot of corrosive products. So we need a very stable crystal. Therefore, we use a diamond crystal. Okay, so just an example of how you see the spectrum. Okay, so in FTIR, normally we record the spectrum in transmittance. Okay, but we can also record the spectrum in absorbance, right? Even if you record it in transmittance, you can convert it to absorbance easily with the software. Or if you run absorbance, you can convert it later to a percentage transmittance. Okay, so both are possible. So you can see the quality of the spectrum on the right side, right? The ATR spectrum. You can see that the fingerprinting region, like from around 2000 to around 500, is very enhanced, right? Because you are not adding anything. Okay, you are not manipulating anything. There cannot be any user or operator error or any mistakes. Okay, just you're placing the sample as such and you're recording the data, right? Okay, so we know that IR source to chemical sample, a sample to detector, right? So the left-hand side spectrum is the spectrum by absorbance. This one, the right-hand side, is the percentage transmittance. Okay. Okay, so whenever we talk about vibrations, you think about two balls attached to a tennis ball. You can say tennis ball attached to a spring, right? So when you stretch it, right, you are going to see when you're stretching it, you're going to see the motion, right? Moving the vibration because of the spring. So that's what we call as vibration. Okay, there is a to and fro. Sometimes the spring is going to get compressed. Okay, so this we call it as vibration. This is only one type of vibration I'm showing here, but there are a lot of different kinds of vibration in a different way possible. Okay, so as long as the molecule is going to be very symmetrical, the vibrations are going to be very symmetrical, then we are not going to get much information out of it. So therefore, always we need to have an unsymmetrical. Okay, so that's what I told in the beginning, like to fish in a pond, you have to disturb the pond to understand what are the different kinds of fish available. Because when you disturb the pond, the fishes move out and you know very clearly. So therefore, we always have to perturb the molecule in a right sense, right? So if a non-molecular, if you see a non-linear molecule, which is having n atoms, okay, so then what are the number of vibrations it can undergo, right? For example, your molecule, you have 4 atoms, right? It's going to be 4 into 3, 12, 12 minus 6, 6. So there's going to be 6 kind of fundamental vibrational modes, which is going to happen in the molecule. So there are some vibrations I have shown here. Okay, so you can see the water molecule on the left. Okay, it's an anti-symmetric. stretch. That means one side it's going down and one side it's going up, coming up, going down. Okay. And then symmetrical stretch, both going up at the same time and coming down at the same time. And then you're also seeing a scissoring bend, right? So you're moving like this. So it's called a scissoring bend. So you can also see the same effects in carbon dioxide molecule. Okay. It's a linear molecule. So therefore it's going to be symmetrical and anti-symmetrical stretch. And there also you can see a bending vibration. You can also see in that kind of vibration. So these are the things which is going to give you different signals in your spectrum. Okay, whenever you see an IR band, okay, you see three kinds of spectrum bands. One is the weak band, okay, medium band, and strong band. Okay, so strong band will be very big, right? You can see the transmittance scale 0 to 100%. Okay, the strong band will be very, very high, almost covering 70 to 80% transmittance. Okay, then medium around 40-50%, and weak will be around 10 to 15% or 20% of the band length. Okay, so not all covalent bonds display IR bond, only polar bonds do so, because as I said, unsymmetrical stretching. Okay, so we can see very easily the output from the molecule. Okay, so strongly polar bonds such as carbonyl group produces a very, very strong bond. Okay, so you're going to see a very, very strong bond in the when you have carbonyl in your system. Like carbonyl means ketones, aldehydes, okay, carboxylic acid, right? And medium polarity bonds, you're going to see medium bands. Okay, weakly polar bonds, we see weak, or sometimes we don't even observe the bands very, very clearly. Okay. Okay. So the next one is what are the applications? What can be done with what information can we get from FTIR? We can see, we can understand the functional group, right? See, even as a in pharmaceutical industry, when they are synthesizing some molecule, right? When they convert any functional group, right? So they can easily see whether the functional group is converted or not just by doing the FTIR. It takes around 30 seconds to 40 seconds to record a FTIR and ATR, FTIR. So it's a very vital tool in understanding whether the reaction has proceeded in a proper way. Even when sometimes we get some very unknown compound, okay, for characterization, okay, even the source is not known, okay, somebody would have left it long time back, and nobody knows, there is no label, they want to find out. Okay, so the first test what we do, perform analytical examination, is through FTIR. FTIR gives you information whether you are seeing an organic framework or inorganic. Then we can check the pH, and then we can identify the unknown molecules also. Okay, so and the second important information is it provides a molecular fingerprint. Okay, so we get a molecular fingerprint about different kinds of vibrations. So each kind of vibration is going to absorb the IR radiation to a different extent. So you're going to see spectrums of different vibrations all through the FTIR spectrum. Okay, so simple terms to understand the region between 3500 to 1600, we call it as a functional group region. Okay, where there is no much peak and we can easily see what are the different functional groups available in your system very easily by understanding this thing by this region. And the next one is a very complex vibration with fingerprint region. It's around 1400 to 600. Okay, so normally people employ sorry, employ mid IR region. So mid IR region covers from around 400 centimeter inverse to around 4000 centimeter inverse. Okay, this covers most of our compounds. Okay, if you see the IR trends, how can the IR change? Okay, so see, if you consider if you keep a cricket ball and a tennis ball on both sides of the spring, like one side is a tennis ball and a cricket, so the weight is different, so therefore the vibrations are going to change. okay, the frequency is going to difference. So therefore, the molecule on either, the atoms on either side of the bond, okay, depending on their heaviness, okay, weight, atomic weight, the frequency is going to change. Okay, you can see CH bonds normally occurs at around 3000. Okay, CD, little bit deuterium is a heavier isotope of hydrogen. Okay, it should come around 2100. If you see CC, then the the frequency decreases furthermore because carbon is more heavier now, and therefore it is 1200 nanometer. Sorry, 1200 centimeter inverse. And again, the frequency also depends on how stronger the bond is. If the bond is stronger, the frequency is going to increase. If the bond is weaker, the frequency is going to decrease. Okay, so that's, so again, we already like in UV, the isolated double bond and the double bond which is in conjugation, that means in alternate pattern, that also is going to change the frequency in a different way. Okay. Oh. So now the normally the whatever we, a lot of people look into alcohol and amines peaks, which is a very strong absorption, which comes around 3300 centimeter. But all these three, alcohol, primary amine, and secondary amine, all the three comes in the same region. Okay, we get around 3300 to 3500. You get, okay, you get a band, very strong absorption. Okay, alcohol will be very strong and rounded peak. Okay, secondary amine will be, the peak will be slightly shorter. Okay, but the absorption is strong, but it will be the height of the peak, the band will be a little bit small and sharp. And then if you take the primary amine, it will have a like a spike on the edge of the spectrum. So it's going to be like a W on the edge, right? So, and if you talk about again, the next important one is about the C double bond O. Bonds are the simple ketones, aldehydes and carboxylic acids. So all of them come around 1710 centimeter inverse. Okay, so it is usually the strongest IR signal. So you can almost see the whole stretch of, when it is present, you can see almost it covers the whole transmittance range of your spectrum, FT-IR signal. Okay, and variations in C double bond absorption. Okay, if it is in conjugated with the C double bond C, then the variation is going to shift from 1700 to 1680. Okay, so likewise, if it's an ester bond, okay, CH, that is COO, and a methyl group or ethyl group, esters, they absorb at a higher frequency. Okay, so everything is going to play a role. Okay, so always the molecule or the bond or atom which we are talking about, the neighbors around it is going to play a very, very vital role in the absorption of the and shifting of the wave numbers in the FT-IR. Likewise, CN stretching bond also normally absorbs at 1200 centimeter. If it's double bond, it's going to be 1660. Triple bond, it is 2200. So this we already seen that as the bond gets stronger, the absorption is going to be on a higher wave number, right? Okay, so this is simply a chart. You can get it in the internet. So some of the applications of FT-IR. Okay, so here we can use FT-IR for trans fat. I remember like a few years back, there was a big consignment in a harbor, and this was containing a lot of chips, biscuits, a lot of things like sweet puff, everything imported from other country, and it's in the harbor now, and they want to find out whether this contains trans fat or not. So they send us random sample to find out whether this is so. So the ideal technique would be to go with a GCMS, okay, gas chromatography, mass with attached with mass spectrum will give you an ideal output out of it. But the time is very crucial. Okay, GCMS, one experiment will take you around 1 hour, and you have to prepare your samples, right? So it takes around 1.5 hours to prepare one sample, one sample. So you have a big consignment of different kinds of samples, including oil, to be analyzed of trans fats. Okay, so the easiest technique, what we suggested to them, was to qualitatively tell them whether we have trans fat or not, because the label says zero trans fat, but the country, before the product coming into the country, the government wants to check whether this is really trans fat 0% or it has any trans fat residue left. Okay, so we were looking into ATR FTR because we know that you don't need any sample preparation, and the trans fat peaks comes around 966 centimeter inverse. The red one, what I marked with the red circle, is where we see the trans fat. And then the other one, the green and the blue ring, which is marked in the blue ring, is the cis fats. Okay, so we are all worried about the trans fats. Okay, so this is a normal spectrum of a trans fat, standard spectrum. Okay, so then we run the sample using ATR FTR and compare the spectrum to see whether you have any spectrum in this region. Okay, so and then finally we found out that these are the different things. So this one was taken from a paper, actually. Okay, from an article. It's not, I did not publish my work. I did not put my work here, direct work here. So they are found in margarine, there were around 3.1% of fat. So if you have a standard and if you can run a calibration curve, okay, you can find out the quantitative amount of trans fat present. Okay, but for the clearance of the product, they need to know only whether trans fat is there or not. Okay, for qualitative, you don't need to run the standards. You can run it instantly. It takes 20, 30, 40 seconds per sample. You can run n number of samples, hundreds of samples in few hours, and then you can send the report, and then the company and the products can be released from the harbor in a short time. Okay, and then the recent much important application which is going on is in the FTAR in microplastics. Okay, microplastics are plastics in the range of 1 micrometer to 1000 micrometer. Okay, so we consume a lot of plastics. Okay, everything, without plastics, nothing is in this world, right? Everything has plastics. So we go to the beach. Okay, we buy eatables, right, in plastic cups, plastic plates. Okay, and eat, and we throw it there. Okay, this gets degraded, and these micro particles, okay, are going to present in the soil, and it's not going to degrade for a very, very, very long time. That's why a lot of push for using a non-plastic products or using a biodegradable plastic products. Okay, so this is one example, which is of the fiber, which is from the fishing net. Okay, in the seashore. Okay, so we can have a standard library. Okay, we can create our own library with polyethylene, polypropylene, and PET, PET. All the three are there. And then we can run our samples. Okay, standard sample. And then you can see a red marked area. That is the region where we can see the decomposition of the or degradation of the product. Okay, as the time goes by, we can see a degradation of the product, heat degradation of the polypropylene. So this can be easily, qualitatively, we can see this. Okay, if you attach a microscope, because the latest innovation in FTAR is the FTAR microscope and FTAR Raman. These are the things so where we can directly see the plastic with microscope, focus the IR radiation, okay, on the place where we want to focus, and then we can get the identification of the particular plastic material, and we can also know from the spectrum whether it is in a degraded form or it is just not degraded. It's a new plastic also. Okay, so even crude oil, like FTR, is now used in crude oil analysis. I did not put the slides in, but you can look up online, that you can find a lot of articles coming up with FTR used in crude oil. See, therefore, the ATR technology has played a very vital role in bringing a lot of different applications which are not possible with a classical FTIR spectrophotometer. Okay. So now into our last topic, nuclear magnetic resonance. Okay, this is one of the NMR which we have in our laboratory. It's a 700 megahertz NMR attached with a cryo platform. So it's a very, very, very top end NMR which can be used to run one-dimensional, two-dimensional, and three-dimensional NMR. Because of the cryo platform, we get a very good, very, very, very high resolution compared to the room temperature probe-based NMR. Okay. So here in NMR, we are going to talk about nuclear transition. Okay, just to revise back, UV, electronic transition, FTIR, we talked about vibrational transition. Okay, and here in nuclear magnetic, we are going to talk about nuclear transitions. Okay, and we are going to talk about electromagnetic radiation, which is nothing but radio waves. Okay, which is very similar to your FM radio station. Okay, so here again, we are going to get a fingerprint, and the spectrum is also emission spectrum. And one of the advantage of this technique is non-destructive and contact-free. Okay, so you can reuse the sample. The nuclear transition is going to be only happening. This nuclear thing is going to happen only in the presence of the NMR, and once the sample is taken out, there's not going to be a change in the sample. Okay, you can evaporate the solvent and reuse the solvent, reuse the sample for further analysis, further study, or whatever you want. So that's one of the idea, and it's contact-free, right? We are not going to touch the sample directly. We're going to use a special NMR tube. I will show you some pictures of it later. And then the modern variant, what we are using is the NMR topography or magnetic resonance imaging. So everybody would have heard about MRI. Okay, MRI is a medical application of NMR. Okay, so if we use patient, then we use MRI. If you use samples, we are using NMR. Okay, so that's the idea behind it. Okay, so not too much into the chemistry behind it. Okay, the main idea is the spin the spin quantum number I should be equal to, if it is equal to 0, then the NMR compounds are not active. Okay, the basic idea is, you remember that I is equal to half. Okay, any atom having I is equal to half. Okay, in the basic level, we can think, we don't need to think about the other 3 by 2, 5 by 2, and etc. But we can think that I is equal to half. Then we are going to talk about this is active in NMR. Okay, so NMR is blind to many molecules, many atoms. Okay, NMR can see only certain atoms which is having I is equal to half. Okay, so that's what we are going to say. See, each atom has electrons, protons, neutrons. Okay, these charged nuclei is going to give a magnetic moment for the particular atom. Okay, so that's the basic. So charged particle brings magnetic moment to the atom. Okay, so when there is no external magnet, okay, the magnets are going to all the nuclei are going to align in different directions, as I shown in the second picture here. Okay, and therefore they are going to cancel out, and the net magnetic moment is going to be 0. Okay, but when you place it in the magnetic field, okay, compound nuclei with I is equal to half nuclei like hydrogen, carbon C13, okay, and fluorine 19, phosphorus 31, they are going to form 2 states. Okay, again we are going to talk about a ground state and a upper state. Okay, an excited state. So this state is created only when the sample is placed in the external magnetic field. That's why you see a very big body around the magnet. Okay, that is the big magnet of the NMR, which is playing a very important role for this sample. So when it's created, okay, there's going to be a transition. They're going to the nuclei, which is in the ground state, is going to absorb the radio waves, okay, and then going to jump to the upper or the excited state. We call it here as the beta state. And then when you stop the radiation, okay, they're all going to come back to the ground state, relaxation. We call this as term as relaxation. And it's going to emit whatever energy it has absorbed, right? So this is going to be an emission spectrum. So whatever you're going to see is going to be, because each molecule, each nuclei is going to release the amount of energy it's absorbed, and it's going to be different depending on the environment. Okay. For example, like I can see now, you're all sitting in the seminar, so you're very quiet, calm, and very attentive, right? So when you are outside with your friend, your behavior is different, right? When you're with your parents, things are different, right? When you are in a religious place, then your behavior is different. Okay, so therefore the nuclei also behavior depends on the surrounding nuclei. Okay, so that's the idea behind the NMR. Okay, in simplest term. Okay, so the high resolution NMRs like 700 NMR, okay, is going to give a very, very, very high resolution output. Why? Because this is the simple reason. Because once the two states are created, the distance between the two states is a very important factor. Okay, because if you have a 60 megahertz NMR, you see the distance between the two states are very, very less. Okay, so therefore the transition which is happening is going to be very quick and very fast and in a nano time scale, and the NMR is not going to pick it up very clearly. Okay, so the transition which is happening in between has to be in a very clear time scale, NMR time scale. Okay, so that's why when we use a 700 megahertz, the distance between them is going to be really high, and there's going to be a very good transition between the, it's going to be captured by the NMR very, very clearly, right? For example, if I'm throwing a ball from a first floor or a second floor of a building, and you are standing down in the ground floor, and then you want to just capture it with your phone, right? Before taking your phone and switching on the video, the ball falls down, right? Suppose if I'm throwing the same ball from a 50 floor or 44 floor building, right? So you will have at least some time to capture what's happening, which color ball is coming in. Okay, what's like you can create a video of at least a little bit of a flow. So because you have the time frame to take the camera, switch on the camera of your phone, and then take the capture. So therefore, this is going to be playing a vital role in getting the final output of your spectrum. Okay, so that's why the quality is getting increased compared to a 60 megahertz. If we compare a 700 megahertz, it's going to be a wide difference. Okay, so this is a normal schematic of a NMR. Okay, so you will have a magnet, and you can see a red arrow on the top. That's where you put the sample in. Okay, and the probe is under. Okay, we'll put the probe from under. So the probe will always attach the magnet from down, and this box on the side, we call it as the NMR console, is the electronic portion of the NMR. Okay, and you can see the picture here. So this is how the sample will be inside the probe. Okay, the probe will have a long head like this. So the sample will go in and stand on the top, and then it will spin in the probe. Okay, so you can see the picture here, right? The spinner and the NMR tube. Okay, and then we have the computer with the software where we can process everything. So since NMR is a magnet, so we have to be very careful with all the magnetic material which is there available in the room. So everything has to be either plastic or non-magnetic material. Normally we use high quality aluminum material for because aluminum is highly it is non-magnetic in nature. Okay, so in the older NMR, the shielding was very, very bad. So therefore, we used to sit in the next room and operate the NMR. NMR, the main system will be in a different room. and the operator will be operating from a different room. Only they'll come in to put the sample in. Now, because of the shielding efficiency, we can sit in the same room and we can run the NMR experiment. Okay, this is a very old geol NMR. Okay, so you can see that this is how it looks inside, and on the right edge, the one is the magnet. Okay, with coils around it. Okay, so there'll be a lot of coil. Okay, it's just a wire. Okay, and the wire is made up of special alloys. Okay, and mostly it's a company trade secret, because this coil is going to be acting as a creating a superconducting magnetic effect for the magnet, because all these magnets have a superconducting magnet. To make this magnet superconducting, so in the inner chamber we fill it with liquid helium. Okay, so liquid helium, the temperature of the liquid helium is around 4 Kelvin. So we will fill the helium there so that the temperature caused by the movement of electron in the coils are going to be removed by the liquid helium in the container where it is. So therefore, the magnet will be submerged in liquid helium, and it provides a continuous superconducting magnetic field for us to run the experiment consistently. Okay, because what is superconducting magnet? Actually, superconducting magnet is the one which is going to, even without any external electric field, electricity, it's going to produce a magnetic field. This was commissioned, I think, in the year 2013. Till now, we are not supplying any electric current to the coil, but it's supplying magnetic field. That's why we call supermagnetic magnetic. Because if you switch on the light, okay, when you switch on, immediately the light comes in. When you switch off, the light off. But here we have already switched off the electricity, but still you have electrons moving around the coil and producing the magnetic field. So as I said earlier, we are going to use radio waves for this kind of nuclear transitions. Okay, so the main information what we get from the NMR is that we are going to get the number of signals. Okay, so we can count the number of signals in the spectrum which I given. Okay, and then we can see the position of the signal. Okay, where the signal is coming also plays a very important role. And then the intensity of the signal. Okay, the area will give you an idea about how many electrons, or sorry, how many nuclei are having the same signal. Okay, and then we will also have a signal splitting. Signal splitting will give you an idea about the neighboring nuclei. Who is the neighbor? Okay, so depending on the neighbor, the splitting will differ. If there is a 2 protons nearby, the splitting will be 3. Okay, always number of proton plus 1 will give you the splitting information. Okay, so I'm not going behind the chemistry behind the whole thing. Okay, so the common NMR spectrum, what we normally use is the proton NMR and the C13 NMR. Okay, see, whenever you talk about C13, why I'm specific in C13? As I told you before, NMR is blind to certain nuclei, which doesn't have I is equal to plus or minus half, right? So C13, C12, and C14. Okay, these are all isotopes of carbon. Okay, so C13 is what is visible in NMR. NMR cannot see the C12 very clearly. Okay. Sorry. So C13 NMR. So C3, if you see the natural abundance, okay, natural abundance also gives a sensitivity to the final output of your spectrum. Okay, so C12 is in a higher concentration in the natural abundance. It's around 98%, 98%, and C13 is only present in around 1.1%. Okay, so NMR is going to see only this 1% carbon. So that's why carbon experiments run for a longer time, and you also need a higher concentration whenever you run a carbon sample. That means we will be using, for example, 5 milligram to 50 milligram of sample dissolved in the suitable deuterated solvent. Suppose your sample is soluble in water, H2O. You cannot use H2O for NMR. We have to use D2O. D is a higher isotope of NMR, the deuterium. So D2O is used as a heavy water. We call it as heavy water, will be used for NMR. So always for NMR, we will not use the common laboratory solvents. We will be using the deuterium isotopically labeled solvents. Okay, all the hydrogen in the solvent has to be replaced by the deuterium. Okay, for hydrogen experiments, the 1H experiment, the sensitive hydrogen contains, natural abundance contains 1H equal to 99.98%. So whatever the NMR is seeing is almost 100% is what it's able to see. So therefore, you can give only 1 milligram to 5 milligram sample, okay, and you can run the experiment in 30 seconds. Okay, so for carbon-13, it takes around 1 hour to around 7 hours in our NMR, 700 megahertz attached to a cryo platform. But if you use a normal RT probe and an RT NMR, then it will take around 13 to 14 hours to get a very good spectrum out of it. Okay. Okay. So this is if you see the right-hand side, I've posted all the types of NMR tubes which we can use. The most common NMR tube what we use is the 5 centimeter diameter NMR tube. Okay, it's a special tube. Therefore, it's very, very expensive. Okay, it's not going to produce any spectrum when you run the NMR. So it is going to be, it is a perfectly pure quartz tubes. Okay, so depending on your application, we can use different NMR tubes. Okay, even we can use 3 millimeter NMR tubes when you are using protein and peptides and where you don't have enough concentration of your sample. Because if you don't have enough concentration, you're going to run the experiment for a longer time. When you're running the longer time, the disadvantage is the noise is also going to be exaggerated along with the multiplied along with your signals. Okay, so you're going to get a very broad base. Okay, and you're going to lose very small signals out. Okay, so that's the importance. Okay, so there are different solvents like CDCl3, okay, acetone D6, and anything you can use. So again, the sample preparation part. Okay, we see the right side. When the good one is that you have to prepare a homogeneous sample. Okay, even if you prepare a sample and if a sample has particles, okay, floating or undissolved particles, then it's better to filter it out and then bring a homogeneous sample, because this solid particles which is present in the sample is going to affect your final output of your NMR. Okay, so even oil, okay, partially soluble sample, if you can see the third tube, then you have the difference in concentration. Okay, 2 different layers, not sufficient amount of solvent. These are all going to play a very, very important role in getting the final output of the sample. So if you want a good result, you have to produce a homogeneous sample. Then you have to give the amount of concentration, okay, to provide the better results. Okay, so this is the part which will be done in the NMR. So we call in NMR term as shimming. Shimming is nothing but making the magnetic field homogeneous. See, when you place your sample inside the magnet through that orange pipe which I showed you, when it goes to the probe, I told you the sample is also is going to have some magnetic field because of the charged particle in them. So that's going to interact with the magnetic field of the NMR, and it's going to disrupt the magnetic field. But if the magnetic field is not uniform throughout the sample where we are looking in, then it's going to affect your system. So therefore, we are going to homogenize using a technique called shimming. So this is all electronic wise. So I'm not going to go more about it. Okay. And the most common ones, what we do is the proton, carbon, and depth NMR. So depth NMR gives you whether your carbon is attached to 1 hydrogen or 2 hydrogen or 3 hydrogen or no hydrogen, more information. 2-dimensional NMR, if you don't get sufficient information from the 1-dimensional NMR, if there is too much of overlapping and so on, you can go for the 2-dimensional NMR like COSY NMR. okay, where proton and proton interaction. So therefore, any overlapping between the signals can be, so it will be in a plot. So you can easily find out the overlapping signals. And if you want to see overlapping signals from proton and carbon, then you can go for HSQC and HMBC, long range coupling experiments. Okay, so for example, these are some of the left hand side is the 2D COSI, where you can see the diagonal is nothing but the spectrum. So the other signals are the cross peaks, which will tell you which peak is connected, which atom is connected to which atom. So this will be useful only when we interpret the 1D data also. Okay, so there are a lot of applications in a NMR spectroscopy, right? So most of the, say NMR can be solution state and solid state. Most of the research purposes we use only for solution state regarding, but the same NMR can, with a small variation, can also go for solid state compound. Solid, like people who are doing material coating, material development, and so many things, films, thin films, and all that can be studied with solid state NMR. So most of the people use for R&D purpose, pharmaceutical, chemistry, biology, and people, all they use is solution state NMR. So we can see a lot of information, molecular dynamics, okay, intermolecular interactions, okay. We can also see metabolite analysis, okay, molecular dynamics, okay. So we can also, by changing the temperature and recording the NMR, we can understand whether the peak is stable or whether the bond is breaking, and everything, all the information we can get from NMR. Okay, so this also I'm not going to go very deep. So some of the very good applications are that we can screen the small molecules with protein very simple. It's a very straightforward experiment, and we can screen it, and we can do a lot of work, and it saves a lot of time. So what is this advantage? Like when you go to the supermarkets, or when you go to the markets where you buy plastic bottles and all that, I don't know whether you have checked the label. So when you check the label, it says 0% BPA or BPA free. Okay, because BPA is causing cancer. So therefore, BPA has to be checked for interaction with protein. So like small molecules are chosen, and different kinds of protein, one protein is chosen, and then all, like you have 1,000 molecules to screen whether these molecules are interacting with this protein or not. Okay, so and you can check within, like in a week's time, you can finish more than 1,000 samples. So it's very quick and straightforward experiment. Okay, just we are going to just see the interaction. The free molecule, the small molecule, the behavior is going to be different compared to when they interact with the protein molecule. Okay, so that is the difference. Again, the environment is going to play a role. So the one which is interacting with the protein is going to show a different property in the NMR compared to the non-bonded one. So you can put 3 or 4 or 5 small molecules with one protein, and at this time you can find out which are the molecule interacting, which is not interacting. So this is very useful in pharmaceutical industry. So they easily screen and find out which is going to interact with which kinds of protein, and then we can study more about it, which site it's interacting, whether it's interacting the main site which is giving the property of the protein, and so on. Like, okay, so the simple thing is narrow line, broad line. Okay, so the small molecule is going to give a narrow line spectrum, and the bound molecules are going to give a broad line. Okay, sometimes in some experiments you're going to see a weak signal. Okay, the signal intensity of the peak is going to decrease after interaction, or it's going to be positive, it's going to be more. Sometimes it's going to come on a different phase, negative phase, and the non-interacted one will be in the positive phase. Okay, so these are the things which we, for example, in this particular experiment called T1 row relaxation experiment, okay, we can see that once it is binding, you can see the red signal coming down here. Okay, the red signal, the red NMR signal at 8.7 ppm is coming down to very less. amount. That means this particular nuclei, particular small molecule is now binding with the protein. Okay. This is just a qualitative test to find whether it's binding or not. Okay. So in this particular experiment called water lodge C, we can easily find out the binding ones will all come to the negative phase, and the positive ones are the ones which are not bonded, okay, which are not binding with the proteins. So we can easily find out which are the small molecules in the solution which is binding to this protein, which is not binding. So that's why it's called as ligand screening experiments. It's a screening experiment. Okay, once you are done with the screening, then you have to go with the 2D, 3D NMRs to find out where is the site bonding, and then we should also use molecular modeling to understand more about the binding sites. Okay, so there is one more experiment called saturation transfer difference. Okay, STD experiments. Here you can see the not bonding ones, okay, the binding ones are increasing in size. Okay, the non-binding ones are disappearing. Okay, so that is also one of the experiments. So these three experiments can be used for screening purposes. Okay, another application is NMR of Sera analysis. Okay, and so this was published along with Dr. Sanket. We worked together in this project together, and we published together. And so this is actually, this crude oil has 4 important components to define the quality of oil. We call it saturates, aromatics, resins, and aliphatics. So aspartans. So the percentage of all these components is going to play a vital role in defining the quality of oil. So the traditional test is very, very costly. Okay, more than $1,000 to $2,000 test, and it takes maybe 1 week to 10 days to get this data. But we can do the same thing with maybe $50. We can do it in the laboratory using NMR. Okay, just recording a proton spectrum, and then from the spectrum, we know that from 0 to 6 ppm is the aliphatic region, and 6 to over 6 is the aromatic region. From that, we can find out the percentage of aliphatics and aromatics, and then from that we can find out how much is the asphaltene, how much is the thing. So if there is more asphaltene, then the quality of oil is going to come down. Okay, so this is how. So we represent the values in percentage. So not only this, we can also get a lot of different types of information from the crude oil, because crude oil is a mixed matrix. Why I'm showing this application? Because in the textbooks, when we read about NMR, always they say that NMR can be utilized only for pure compounds, single compounds, structural determination, characterization of an unknown compound, and all that. But NMR, due to the latest application, latest innovations in NMR technology, we can also use for matrices which are not pure, mixtures. Okay, so crude oil is a mixture of hundreds of different kinds of aliphatic components. Okay, aliphatic and aromatic components. Okay. The next one is the DOSI experiments. So DOSI experiments are very, very, DOSI means nothing but diffusion experiments. For example, I have shown one example here. Acetaminophen is nothing but paracetamol. Okay. So to find the impurity in paracetamol, normally we use HPLC techniques. But HPLC techniques take a long time. You have to ascertain the method. You have to find the right column. You have to make the method development, and it takes a long time. But in the NMR, just dissolve the paracetamol in a suitable solvent and run the sample in this NMR. Okay, within 10 minutes, you are going to see the result like in a graph here shown here. Okay, the acetaminophen is going to come at a different level, and the dextrine, which is used as a binder, is going to come at a different diffusion. The idea behind this, each molecule in solution is going to have a different diffusion. Okay, so this different diffusion So acetaminophen is different, dextrin is different. So it's showing a different in diffusion. So that's what we are seeing in the spectrum. So acetaminophen comes in this diffusion, and then this is having a different diffusion. If the diffusion property of both the mixture which you are evaluating is almost similar, then we cannot use this kind of technique. Okay, so this is also very important. Then we can use three-dimensional NMR for protein characterization. Okay, and we can also use it for application in metabolomics, because now the chemometrics techniques are coming out very handy because of the development of a lot of molecular modeling and a lot of software-based support for NMR. So we can use this kind of data from NMR and extract different kinds of information. So now, recently we are working on samples like in concentration of different amino acids, different chemicals or different compounds present in plasma. Okay, with NMR we can easily find out. So collect the data, and then we can put it into this chemometric software, and we can get the percentage of we can get the concentration of each and every different substrate or sample which we are compounds which we are looking for. Okay, so it's very simple. So otherwise, previously we have to do through HPLC separation, so many things. So it's very straightforward. It takes only 1 or 2 minutes to run the NMR and then putting the data into the final output. Okay, so this is a very vital role. So not only this plasma, but we are also working now with honey. Is also a very important factor in Oman, because Oman synthesized, the country where I'm working in, they have a lot of honey industries. Okay, so they want to import it to the foreign other places. So then they need to know the composition of honey before putting it in the market. Okay, so the traditional technique for checking the quality of honey is to just see the pollen to see the origin, and then depending on the origin, the prices also will depend. For example, there was a case recently, like in one company was selling a honey. Okay, and especially why I'm telling this is, especially after the COVID-19, a lot of people are into taking honey in the day-to-day diets. Okay, thinking that honey is antibiotic, okay, antibacterial property. Yes, really good. It's really good. Even I do take it. Okay, but if you see the original, if you see the statistics, the consumer intake is very high compared to the production. The production has not changed. So therefore, one honey was tested in a traditional method to check whether what is the origin of the honey. So they labeled that honey as Brazil honey, because the pollen grains which they found in the honey was from Brazil, but actually the original honey was from China. Okay, so there are a lot of things going on in the world. Okay, a lot of adulteration is going on in this world, right? So therefore, the people who are adulterating also knows what techniques we are using to find out. So therefore, the targeted analysis are not playing a very important role nowadays. So they need a full screening, non-targeted analysis. Therefore, now people are looking into NMR as a potential source, because NMR can see everything inside the honey. And this company, the company Bruker, has their own database of honey, but it's a very expensive one. So they told the company, okay, we will check and see whether the purity of honey is same or not. And they checked and finally found out that the pollen is from Brazil, but the honey is from China. Okay, so they just purchased pollen from Brazil and they added it in the honey. Okay, so there are a lot of adulterants which is going on, which can be easily detected with the help of nuclear magnetic resonance spectroscopy. Okay, so this is the idea behind it. This is my last slide. Okay, so the main idea behind the NMR is highly reproducible. Okay, so you don't need to worry about reproducibility. Okay, as long as you don't contaminate with a contaminate solvent or something, you're going to get the same result even after 10 years or 5 years running the same sample at a different level. Okay, minimum sample preparation. So that is one key thing, because sample preparation is where we induce a lot of impurities into your system. Okay, and it's a non-destructive technique, so therefore you can just evaporate your solvent back and then you can use it back for other purposes. And then we have a we cannot say very good sensitivity, but we have a modest sensitivity, which is enough for us to do it. So, and for doing this kind of analysis, you don't need a 700 megahertz NMR. A 60 megahertz NMR itself is enough, because you are just seeing the overall profiling of your sample. So you don't need to see exactly whether the sample is clearly split into doublet or triplet. That information is not needed. You have to see one signal for each and every substrate present in your sample. Okay, so you don't need, you can use higher sample volume. Okay, and expensive, it's very less expensive compared to the other mass spectrometric technique. Thank you.
Thank you, Dr. Prem. You have covered everything from UV, visible, IR, NMR, nuclear magnetic range, and everything. So we were supposed to take a break at 11. So इन लोगों का लाइट थोड़ा डिम हो गया और उनके जो मॉलिक्यूल्स है वो रेजोनेट नहीं कर रहे, बहुत ही लोअर फ्रीक्वेंसी पे रेजोनेट कर रहे हैं. सो अगर आपको कोई क्वेश्चन है, यू कैन आस्क नाउ और यू कैन सेंड हिम एन ईमेल. दे डोंट हैव एनी क्वेश्चन. बहुत ही अच्छा समझाया आपने, और मे भी शायद कुछ भी समझ में नहीं आया उनको. So thank you very much, Dr. Prem. So हम लोग ने काफी अच्छा काम किया था when we were together. I am not a chemist, I am a microbiologist. वहाँ पे जब 15 साल साथ में थे, हम लोगों ने बहुत सारे नए टेक्निक्स डेवलप किए थे for NMR. Like one of the thing what we developed together was for oil companies. जो एक सैंपल, एक क्रूड ऑयल का एक छोटा सा सैंपल एनालिसिस के लिए आता है, it takes around week or 2 or something. This is how we used to do analysis, SARA analysis in the lab, and we made it not quite cheap, but quite faster and a much economical rate. Our group was the first group जो वर्ल्ड में ऐसा टेक्नोलॉजी और सब लेके आए थे. And now most of the companies and all, they are using it. हनी के लिए भी काफी सारा रिसर्च किया था. So this is what I was talking about in the beginning, multidisciplinary work. Like he is a chemist, but he is also working and doing things in biology, in physics, and different things. I'm a biologist, but I'm also learning new things and all. So multidisciplinary is the new thing. So thank you, Dr. Prem.
Yeah, may I add few words?
Yes, please, sir.
Dr. Prem, you made a great presentation actually, and you explained everything about the working of the machines, the optics behind their working, physics behind their working, and also a little bit of chemistry behind analysis. So all these things are very important. And above all, you explained very well various applications of UV visible to NMR, IR, FTIR, all these technologies and their applications was very, very nicely explained. And that speaks about volumes about your experience which you have with these instruments. And these trainee students are novice, and they will learn when they get more and more exposure, and they will use these instruments in their research work. So I think I'm extremely delighted that a person like you explained the working of all these instruments. Thank you very much.
Thank you, Professor Kothari, and thank you, Professor Sanket, for giving me this opportunity. It was like I really enjoyed this presentation with you all. And so I've just given you small applications, little applications, but you can find lots application and you can work it. And as Dr. Sanket already told you, like interdisciplinary research is the key now. So don't think that you're a biologist, you should not know chemist. So you can just look into all this, and this will be a very fruitful future for you. Thank you. All the best. Thank you.
Dr. Prem, whenever you are coming to India, please do visit us, and
yes, definitely
take care of your local hospitality here.
Okay, definitely, Professor. Thank you, Professor. Thank you.